Hello there, my name is Lane Pratt, and today I will be discussing general relativity, gravitational waves, and LIGO, otherwise known as the Laser Interferometer Gravitational Wave Observatory. Here are some things you should know about general relativity. Firstly, in general relativity, all experiments conducted in a uniform gravitational field and in an accelerated frame of reference give identical results. Secondly, Albert Einstein determined that both space and time are relative. The speed of light in a vacuum is constant, however, and is represented by c, which has a velocity of around 3 times 10 to the 8th meters per second. When Einstein came up with this theory of general relativity, he also developed a set of equations. The time dilation equation can be written as delta t equals delta t naught divided by the square root of 1 minus velocity squared divided by the speed of light squared. The length contraction formula can be written as length equals length naught times the square root of 1 minus velocity squared divided by the speed of light squared. The relativistic energy formula can be written as E equals mc squared. Now let's go over gravitational waves. As Albert Einstein described in his general theory of relativity, gravitational waves spread at the speed of light, filling the universe. We know what their velocity is, but what exactly are gravitational waves? A simple explanation is that gravitational waves are ripples in space-time caused by violent collisions or explosions of objects in space. A real example, the first ever being measured, is the gravitational waves produced by the colliding of two black holes that took 1.3 billion years to arrive on Earth, but more on that later. To better understand gravitational waves, I made this model. As you can see, the smaller ball orbits the golf ball until the two collide. It might be hard to notice, but these divots in the fabric that represent gravitational waves warp the fabric all the way to the edges of the box. If a denser object was placed on the model, the divot, and thus the warping, would be greater and reach further. Up until a few years ago, scientists could only prove the existence of gravitational waves using mathematics, but all that changed on September 14, 2015, when the first gravitational waves were measured with LIGO in the swamps of Louisiana. To measure gravitational waves, LIGO was constructed. Measuring gravitational waves is an extremely hard task, since conventional forms of measuring would not work. As an example, I have assembled this contraption. I have placed two rubber bands next to each other and connected them with tape. One represents the object being measured and the other represents the device doing the measuring. I will demonstrate the effect of gravitational waves as I pull. When I pull, you can see that both rubber bands are stretching, meaning that there would be no way to tell that they were warped in the first place if something like a measuring tape was used. LIGO solves this problem in a genius way, however, by using the constant speed of light to measure warps in the spacetime. LIGO consists of two 4-kilometer-long tunnels that are perpendicular and works by measuring how much those tunnels warp. Lasers are beamed down each tunnel and bounced back by mirrors, essentially acting as a ruler for the arm. Sensitive detectors can tell if the length of the arms of a LIGO detector varies as little as 1/1000th of the width of a proton, representing the incredibly small scale of the effects imparted by passing gravitational waves. On September 14, 2015, for the first time in history, gravitational waves were measured. These gravitational waves took 1.3 billion years to reach LIGO, and it was concluded that they originated from the collision of two black holes, thus proving that Einstein was correct and physically proving the existence of gravitational waves.